Welcome back. Today I want to talk about a special kind of circuit, which is known as an RC circuit. And I know what you're thinking to yourself. If I have an RC circuit that has both a resistor and a capacitor, how can there be any interesting circuit dynamics? After all, charge can't flow through a capacitor. And while it is true that charge can't flow through a capacitor, I can still have current through a circuit as that capacitor is building up charge, and therefore there's charge flowing through the circuit in order to build up the charge, or there's charge flowing through the circuit to decharge the capacitor. And so I'm going to set up a circuit where I have a battery that has some fixed EMF, a switch that allows the resistor and the capacitor. The resistor will have resistance R and the capacitor will have capacitance C. But the switch allows current to flow through the resistor and the capacitor and come back to the battery. So when I close this circuit, and that is I take this bar and I make the circuit closed here, I end up with just one loop around which the current can flow that goes from the battery to the resistor to the capacitor. If I set up Kirchhoff's loop rule, I'll start right below the capacitor here. I'll assume that the current is flowing through the circuit in the clockwise direction. Again, this may be wrong, and I'll just get a minus sign when I finally solve for the current. Given this guess for what the current is doing, the potential is going to drop across the resistor. So I'm going to put my plus sign on the left and my minus sign on the right. And then the potential will also drop across the capacitor. So I'll put my plus sign on the left and my minus sign on the right, my plus sign on top and my minus sign on the bottom. So when I set up Kirchhoff's loop rule, I get, starting again at this point, going clockwise through the circuit, first I hit the battery, which gives me a positive EMF. Then I hit the resistor, which gives me a drop in potential equal to IR. Then I hit the capacitor, and I have an additional drop in potential that's equal to Q over C. The charge buildup on the capacitor at that time divided by its capacitance, and then I get back to where I started, which is 0. And right, we have to remember that this expression here is one that tells me about how the potential is changing around the circuit. So even though charges can't go from one side of the capacitor to the other, there is still a potential difference across that capacitor, which is going to vary depending on how much charge is built up on it. I actually have ended up with a differential equation, and I can see this if I remember that current is defined to be the change in charge with respect to time. And so I can convert this expression to say that the EMF minus dq dt times R minus Q over C is equal to 0. This expression here is in some ways the end of the physics, right? I've used conservation of energy. I've used Kirchhoff's loop rule to give me the relationship between the potential differences across each unit. And now, instead of casting it in terms of solving for the charge, I can cast it in terms of solving for how much charge is built up in the capacitor. And now I have a differential equation. That is, if I wanted to solve for Q, I have to undo some of these derivatives in this expression. But I can use the theory of differential equations in order to solve for Q as a function of time. Now there is one trivial solution, which is if I just go to the steady state where Q is equal to the total charge that's going to be set up, and if I happen to have that charge on the capacitor at the beginning, then there's no current whatsoever. But that's not terribly interesting. So we're going to start in the situation where there really is no charge built up on the capacitor at all. I've written down a couple of the first lines of math here, but I can take my expression and I can now solve it for dq by dt by rearranging some of the terms. And once I have that expression where I have dq by dt on the left plus a constant and things that are functions of q on the right, I can use a method of solving differential equations called integrating, by which I take the dt, I move it over to the right-hand side, and therefore I have a left-hand side that depends only on q and a right-hand side that depends only on t. Of course, the right-hand side depends only trivially on t, but it still only depends on t. So I can integrate both sides of this, where my starting point is, as we've defined before, starting where q is equal to 0 and going to the final time where q is equal to capital Q, which is going to be some function of time. And since I'm starting it at t equals 0, I'm going to go to some final time, which I'm going to call capital T. Now the right-hand side of this is pretty easy to integrate, right? There are no t's, and so all I'm doing is I'm evaluating the integral of dt from 0 to t. The left-hand side, on the other hand, is a little bit more complicated, and it's going to require a u substitution, where I let u equal q over c minus the EMF, and so du is equal to dq over c. If I do this substitution, then I end up with c integral from minus e, right, that's where plugging q equals 0 into the lower limit of integration helps, to q over c minus e, du over u is equal to minus t over r, right? And I've actually done the integration on the right-hand side just because it was so easy. And now I can see that I'm going to get a natural log out of this because I'm doing the integral of du over u, and that thing is going to give me the natural log of the top over the bottom, which gives me the log of q over c minus e over minus e is equal to minus t over rc. And two interesting things have happened here. One is that I, for the first time in this problem, have seen the combination RC appear. And if I do the unit analysis, it turns out that a resistance times a capacitance gives me a unit of time. And therefore, RC is really the time constant of this circuit. It sort of represents how I would naturally measure time. And I get something on the left-hand side that's unitless. And that unitless thing then sort of represents how I should really be measuring charge, right? It's really charge over capacitance divided by a potential is going to be the unit that I can measure the charge building up in this system. And so if I take the last step, I can actually solve this for q over c is equal to the EMF times 1 minus e to the minus t over rc. Okay. Right? By undoing the natural log, I get something that has an exponential. And so what this is saying is that if I plug in t equals 0, I get that e to the 0 is 1, and therefore there's no charge built up on the capacitor. But as I go to t equals infinity, e to the minus infinity goes to 0, and I end up with all of the charge built up on the capacitor. So as a function of time, this is going to start at 0, and it's going to asymptotically approach this value of q over ce, which represents sort of the maximum possible charge that's going to be built up on the capacitor. And so this, as I said, is interesting both because it really gives me a qualitative description of what's going to happen to the charge. It's going to start by growing really fast, and then it's slowly going to grow as t goes to infinity. But it also has this natural time constant in it that sort of sets how long I have to wait for that to happen. So if I set up an RC circuit, I actually can guess how long it's going to take to charge up this capacitor just by calculating this time constant RC, and that's really going to set the scale of the problem. This is one of the first times that we've seen natural combinations of units start to set a natural scale for the problem that I'm interested in. If I, of course, wanted the current, I can go one step further and say that the current, which is dq dt, is just going to be the derivative of this expression, which is going to give me, let's see, I have to, in order to take dq dt, I have to move the c and e to the numerator, and so I have c times the EMF times the derivative of e to the minus t over c, which is e to the minus t over rc times 1 over rc by the chain rule, which is just equal to the EMF over R times e to the minus t over RC. And this expression is interesting too because if I plug this in for t equals 0, I get that the current is just equal to the EMF over R, which is something that I got from a very simple circuit in class the last time we talked. And so I start off in a place where it doesn't seem like the capacitor exists at all. But then as soon as the capacitor starts to charge up, as soon as the potential difference goes from being across the resistor to the potential difference being across the capacitor, I see that the current in the circuit is actually decreasing as the circuit becomes more like a circuit dominated by a capacitor and less like a circuit that's dominated by a resistor. Okay, now that we've charged up our capacitor and we put some total charge Q on it, we can find out what happens when we take this switch and move it so that the battery is eliminated from the circuit, and now I just have the capacitor hooked up to the resistor. Of course, the two sides of the capacitor still have the same potential difference. After all, there are charges built up on the capacitor that give it that potential difference. But now, since the top of the capacitor is positive, current is going to probably flow through the circuit in the opposite way. That is, it's going to flow through the resistor from the right to the left. Therefore, the right side of the resistor is at a higher potential than the lower side of the resistor. I can employ Kirchhoff's loop rules. I'm going to start at the lower right-hand side, and I'm going to move counterclockwise through the loop. The first thing I hit is the capacitor, which has Q over C as its change of potential. Then I hit the resistor, which is going to drop the potential by I times R, which is equal to 0. Or if I want to solve this, if I want to eliminate the minus sign, I can say Q over C is equal to I times R. Now, this might be the end of it because, after all, my current is going to be defined as the change in charge divided by the change in time. But I have to be a little bit more careful in this case. Q, the variable that I'm interested in studying this problem, is the charge that's built up on the capacitor. And what's going to happen here is that the charge over time is actually going to decrease. And so the current that's flowing through the circuit represents how much charge is moving, but it's how much charge is moving, how much charge is decreasing, right? How much charge is leaving the capacitor. So there's an additional minus sign in this definition because I'm talking about how the current is the rate of change by which charge is actually leaving the capacitor. And so if I incorporate that, I get that dq over, dq dt times r, now I have to add that minus sign if I'm plugging in for I, is equal to q over c. And because I was trying to do two steps at once before, I've rearranged the two sides of the equation, but let me now do the second step, which is to move all the q's to one side and move everything else to the other side. I have dq over q is equal to minus dt over rc. And of course, that time constant comes up again in this picture, r times c. It's the only way that I can combine things to get units of seconds, and therefore it's really the only thing that could appear on the right-hand side of this equation. This is a lot easier to integrate than my last expression, right? Because I can just take the integral of both sides. I don't even need a u substitution. But I do need to be a little bit more careful about what the endpoints mean, because my starting point is not at a charge equals 0, at t equals 0, but rather at t equals 0, I have a total charge q that's built up on the capacitor, and I end with some final charge qf at some final time t, which tells me that now the natural log of qf over q is going to be equal to minus t over rc. I can invert that. Natural log, and I can get that qf is equal to the original q times e to the minus t over rc. None of this should be surprising at this point, that I start at t equals 0 with some charge q, and that's going to exponentially vanish as time goes on. Now, of course, the charge built up on the capacitor is proportional to the potential across the capacitor, so I can rewrite this as the final potential across the capacitor is equal to the original potential times e to the minus t over rc. And this is just something that's a little bit more interesting to plot, because if I plot the ratio of the final potential compared to the beginning, what I see is that I start off where the final potential is equal to the beginning, and then it dies off as t over rc. And of course, the time constant is the same as before. The amount of time over which it takes for this capacitor to discharge is the product of the resistance times the capacitance, right? That's the natural scale of the problem. And therefore, no matter what the resistance or capacitance is, I can calculate about how long this thing is going to act as a battery. Of course, because the potential drops so quickly, exponentially so, this thing is not a very good battery for very long. Although perhaps if you were doing some sensitive electronics and needed to stabilize a battery, this would be a good option to add to the circuit. Okay, so the take-home messages are first, that this combination RC appears in the circuit as a natural time constant. It's the things that combine together to set the scale for the problem, insofar as times are concerned. You can have current through a capacitor, although not for very long, right? Because charges still can't flow across from one end of the capacitor to the other. Charges can't traverse that gap, but current can still flow through the circuit. And capacitors can act like batteries in that they can cause currents to move through circuits, but they're just really terrible ones.